screen right here. So let me start recording. And now, right, so I hope all of you can see a black and white image now on your screen. And can one of you confirm me about this? Can you see an image now on your screen, a black and white image?
Yes, sir, we can.
Hello?
Yes, sir.
Okay, right, thank you. Right, so the image that you see right here is an image of a galaxy cluster called l10. I mean, even if you go and search, you will see this. So this is called l10 galaxy cluster, and this was, if I can't remember the exact distance from here. It should be. I'm sure that it is more than 400 million light years away from us. And this particular cluster image is taken by myself actually, I guess 4 or 5 years ago, from this one of these large 4-meter telescopes in Tucson Mountains. And so what I need to show here is all these the large white circles that you see on the image are actually galaxies in this picture, right? And the reason that I decided to select this particular galaxy cluster is that this is one of the very rich galaxy clusters that I have seen, that I imaged myself. And to make it a bit clear, so let me just change this scale so that you will see things more clearly. Change this scale, and if I so this image itself is actually around 300 to 350 megabytes, and a very high resolution image. And you can see right at the center right here. So if I maximize it, right here at the center is a very bright elliptical galaxy. And this is what I have mentioned to you last Wednesday, that in each and every galaxy cluster there is one very bright elliptical galaxy at the center, and this is an evidence for that. And for almost all the galaxy clusters, if you imaged those, right at the center there will be a galaxy like this, right? And this particular these galaxies are called brightest cluster galaxies, or BCGs. And for any galaxy cluster, there should be one of these galaxies, and rarely there are two of those. Sometimes there are two galaxies sometimes that close to the central region. I remember that I have seen like one or two galaxy clusters like that. And apart from that, actually this particular galaxy is pretty unusual, in the sense that this particular galaxy had a lot of H alpha emission, even though it's an elliptical galaxy. And actually, I don't have time to show you everything, but so I have taken the same image from two filters. If you remember that we talked about these filters, how they work at the very initial lectures in astronomy, right? So this particular galaxy cluster I have imaged using two filters. One is called red band filter, which is the red wavelength, and the other one is called the H alpha filter, which is a very narrow band that gives you only the H alpha flux that comes out from this particular galaxy. And I have seen that there are a lot of H alpha flux that coming out from this particular galaxy. And when you see H alpha, that means actually there are a lot of star formation going on inside the galaxy, right? Normally, the elliptical galaxies, we used to tell that they are kind of older stars, that you don't have much star formation going inside these galaxies, but this is one of those galaxies that I have seen pretty unusual. And the other galaxies, now you can see that when I just zoomed out this one close to this central region. So let me see if I can mark regions here. Yes. Close to these central regions. So here is what you can see as the BCG galaxy, but if I take a larger section like this, and you can see that close to the very center, you can see there are a lot of galaxies, but almost all of them are elliptical galaxies. Surprise. I mean, this shouldn't be a surprise for you if you remember what I have mentioned you last Wednesday, that when you take a one galaxy cluster, most of the galaxies that you are observing close to the central region of the galaxy cluster are elliptical galaxies, right? And that's a feature of almost all the galaxy, almost all these galaxy clusters. And you can see that there is all these galaxies right here. If you maximize a bit more, so all these are actually elliptical galaxies, and you cannot even observe directly any spiral galaxy in this region, right, close to the central region. And but if you go a little bit into the outer region, let's see. You can see right here when you so let me zoom it the outer region, and here are elliptical galaxies right here, and there is one. So let me minimize. Here is one spiral galaxy right here, right, and here is another one right here. So what I am circling here, all of them are spiral galaxy, and you can probably see that there are spiral arms, right, very clearly. And yes, when you go a little bit further out, you will see more and more spiral galaxies, right? So I'm not going to show you all these things, but if you need to look at spiral galaxies, then it's better that you probably looking at a little bit towards the outer region of the galaxy cluster now. So if I just maximize one of these galaxies, zoom one of these galaxies. You can see that this one right here is clearly a spiral galaxy, right? So you can even see the spiral arms. And the other one right here is this particular galaxy right here. So what I'm doing here is just zooming into each galaxy, and you can see this particular one. So it's very clearly a spiral galaxy again, like that. When you go to these outer regions, you will see more and more spiral galaxies, right? So this is also called as the morphology density relation in extragalactic astronomy, which basically means that you will see more elliptical galaxies towards the central region of a galaxy cluster compared to the outer region. When you go for the outer region, you will see more spiral galaxies. Okay? And there are different interpretations for this, but I mean, that is the idea. And by the way, when you look at these images, you will see that these images not as the same as what you see in the internet sometimes, right? Colorful images. And these are actually scientific images that are taken for scientific analysis. But if you need to make a colorful image, what we normally do is you take the same galaxy cluster using few different filters. For example, you can take the same galaxy cluster through a red filter, green filter, and blue filter, RGB filters, and then you combine all these filters together to make a color image, right? That's how you make you normally make these color images. But for the scientific purposes, this is an image that is directly taken out from a CCD camera, right? And so if I remember correctly, the exposure time for this image is 5 minutes, which means you open the shutter of the camera for 5 minutes to get this image, right? And that's why you can go more and more deeper. And what happens is that since you are looking at galaxy clusters, these streaks right here, or this one, and this one. So these are actually very nearby stars in our own galaxy, right? And these are very bright stars. What happens is when you use one of these very large telescope with a very high quality camera, so these stars that are very bright and close to us, they get saturated, right? So what happens is they get saturated. So that's why you see these streaks of lines that goes out from the star, right? That is because basically that particular pixel cannot handle all this light coming into that particular from that particular area of the sky, so that so it will basically go or distributed to the other pixels, so that you will get a saturated image. All these streaks that you see right here, so they are actually saturated stars, right? And this one right here is the same region, and all of them are actually saturated stars. Now you can see that the exposure time that we have to use for a particular image, and I mean how long you should look at, and which camera and which telescope that you should use, that all depends on your purpose, right? For example, if you are looking at stars close to our galaxy, I mean within our galaxy, this image is actually not a good one, because all these bright stars within our galaxy are already saturated. Saturated means they are overexposed, and you cannot even use those for a scientific work. But for me, what I was doing is actually measuring some of the star formation properties of these bright galaxies. Even I was looking at this set of galaxies called dwarf galaxies specifically. And because of that, these particular stars are not important for me, my research at that time. So I didn't care about whether they got saturated or not, right? Because what I was trying to look at more and more into deeper objects, which are millions of light years away from us, right? So when you do it, these front objects on the within our stars within our galaxy, especially these very bright stars, they automatically get saturated, right? I mean, I just answered that because I remember that sometimes students used to ask this question: what are those things that you see in this image? And you probably will see that for this for the general public, sometimes they get these images and make these saturated stars even nicer by color coding those, and they look beautiful in these color pictures, right? But for the scientific purpose, you cannot use those saturated stars, right? Well, that's just one example, and let me see whether I can open up another image, just one image, and then I will go back to my presentation after that. And by the way, if anybody needs to know, this particular software that I am using to open up these images is called DS9. And there are similar kind of softwares like this. Probably some of you know that this Astro Image J, those softwares are pretty much similar to what I am using here. And see whether I can show you another one such image, and then I will go into my presentation. Right, so here is another image, image which we share this. And I hope you should be able to see that particular image. And this is called a l10 galaxy cluster. And here is how it looks like. And you probably see that there are, black, dark regions which are, you cannot see anything, those kind of things. Those are actually practical issues because these images are taken from a CCD camera, which you have several CCD chips connected together. And actually there were around 8 of those chips connected together, and 8 or 16, I cannot remember. And so because of that, when you observe the images, you have to observe it, by shifting the telescope a few times here and there, and then you stack all these images together. And still, sometimes you have to face this problem with the gaps between CCD chips. I mean, those are actually some technical issues that you don't need to worry at this point. What I want to, let me smooth this image a bit, show you some of the features again. Right, and once again, you can see that once I smooth this image, right at the center, here is this DCG galaxy right here, as you saw in this previous image. And then all these objects in this region, on the central region, again, you can see that there are more elliptical galaxies, right, at the central region. But when you go for these outer regions, you will see with more spiral galaxies. For example, here is a spiral galaxy right here. I hope that you can see the spiral arms. And so like that, I can zoom out in different regions and show you actually different regions to see whether we have some spiral galaxies. Right here, you can see a nice spiral galaxy. Right? I mean, unless you zoomed it, you don't know whether it's a spiral or not, because these are very high resolution images. There is another spiral galaxy right in the outer region, in the galaxy cluster. So if you zoom it out and so change the scale bit, you can clearly see the spiral arms of the galaxy, right? And these are actually around, close to 1,000 to 2,000 million light years away from us. And you can see the beauty of the technology that we have. I mean, just think about something like this that we image from the Earth, which is like around 2,000 million light years away from us, right? And still you can zoom out and look at these spiral arms and everything, right? So that's how actually these images looks like, right? So I just want to show you how they looks like. And so let me finish sharing this and go into the presentation. Right, so I'm not going to go through like each and everything, but I will show you some of the important things here just to give you an idea. So, screen mode. Share, I think. Right. Now, so I assume that all of you can see the screen, and this will probably be a nice way to see that what you would, I mean, if you go for like more higher studies in future, what kind of things that you will end up, right? And so my topic was actually exploring the star formation in cluster galaxies. So that was basically the idea is you are looking at galaxy clusters and then specifically look at how the stars are forming inside these galaxies in galaxy clusters, right? Specifically in galaxy clusters, right? So that was the idea. And then they were like, so I have, this is by the way the original presentation I did for thesis defense, and so I have an introduction part, observations and data reductions, results, conclusions, and acknowledgements. And to start it, this is what I have shown you, the Abbe 426 galaxy cluster. And this particular galaxy cluster, this image actually is not the same image that I showed you, and this is a color-coded image taken from the Sloan Digital Sky Survey, because they had the same image, and you can see that this image looks beautiful, right? And this is right here is what was that brightest cluster galaxy that I showed you in the black and white image, and all these streaks that you see in some of these objects are actually saturated nearby stars. Other than that, these objects, this one, all these are actually galaxies, and this particular image only have the central region of the galaxy cluster. And the redshift of this particular galaxy is 0.018, and if you convert it into a distance, that will be 78 megaparsecs, and in terms of the light years, that will be 3 times 10 to the power 6 light years, right? That is the distance from here, and in terms of miles, that will be 2 times 10 to the power 19 miles, the distance to this particular galaxy cluster. And this is one of the clusters that I have imaged. And so here are some actually very specific details about galaxy clusters, and some of them we have not discussed, but from this particular slide, you can learn some of these properties. Basically, these galaxy clusters are the most massive, mainly visualized structured in the universe. I think we talked about that. And there are hundreds of thousands of galaxies bounded together by gravity inside these galaxy clusters. And a typical mass of a galaxy cluster is more than 3 times 10 to the power 14 solar masses. And normally these clusters are very strong emitters of X-ray, right? Because of that, you can use X-ray telescopes to identify galaxy clusters. Now, that is probably one of the things that we didn't talk much in our previous lecture about galaxy clusters. And then you have actually gas between these galaxies. You have the galaxies inside the cluster, and then you have some kind of gas between galaxies. And this particular gas is called as intra-cluster medium, right? And those are the things actually that should be new for you. And this intra-cluster medium normally consists of normal matter. That means, you know, the normal matter that we know, right? And I was actually looking at basically dwarf galaxies. I mean, that is one of the main concerns for me. I was looking at dwarf galaxies inside these galaxy clusters. And because of that, I have mentioned some of the properties of dwarf galaxies here. So they are small in terms of their size and their luminosity is low. And then they have a faint surface brightness. And as an example, the Large Magellanic Cloud, as I mentioned before, is one of the most massive nearby dwarf galaxies. And dwarf galaxies are also divided into these ellipticals, irregulars, and those kind of different categories. And the problem with these dwarf galaxies is that since they are, you know, very low in the luminosity, they are not very easy to detect. Right now, this is why you need a good camera and a very good telescope to look at these particular galaxies inside galaxy clusters, right? And this is called the morphology density relation. So this is what I have been discussing with you, that this particular graph shows you from this, just look at this blue line and the red line, maybe that will be easier for you. The blue line is called as the early type galaxies. That early type means basically spiral galaxies. So the spiral number of spiral galaxies as a fraction goes up when you go from the center of the cluster towards the outer region, right? Now this axis is called R divided by R virial. So R virial means the virial radius. So that is kind of normalizing the distance. So that's what they have done here. But the basic idea that you need to get here is when you go from center towards the outer region of the galaxy cluster, the number of spiral galaxies increase as a fraction, right? So that's what I was trying to show you from those original galaxy cluster images. And then if you look at the elliptical galaxies, those are these early type galaxies, this red line. These elliptical galaxies, initially the fraction is larger compared to the spiral galaxies, but when you go for the outskirts or the outer region of the galaxy cluster, the number goes down a little bit, right? And this specific relation that you can see in each and every galaxy cluster is called as the morphology density relation, right? So this is something very, very specific to galaxy clusters that you should, I guess, remember. And then you have different types of collisions between these galaxies. So let me skip that part because we talk a bit more about those in previous images. And here is a nice image that shows you what happens when you have these collisions between galaxies, right? Now this is called the cartwheel galaxy, right? And you can see it's like a cartwheel here. And the idea is this galaxy, we believe that it has probably collided or have some interactions with the two galaxies that you see in the outer region. And due to these interactions, this is the image that is taken from this Galaxy Evolution Explorer. And this is an ultraviolet image. So that's why you see that these lot of purple colors in the outer region of the galaxy, which is an indication that because of these interactions or collisions between galaxies, there is that has led to a burst of star formation, right? So you have interstellar matter inside these galaxies, and this interstellar matter is triggered to make new stars due to the collisions between galaxies, right? So that's what has happened here. The reason that I have put this particular image here is my study is, basically related to this, because what I was trying to do is look at the star formation inside galaxy clusters. So if I see a burst in the star formation in some of these galaxies, then I probably can conclude that there may be more collisions between galaxies, right? So something like that. And inside these galaxies, we actually believe that something like this, there is interstellar matter that you have in a galaxy. And then once this particular galaxy moves through the intra-cluster medium, that means inside the galaxy cluster, you have the intra-cluster medium. And if there is a galaxy that moves through this intra-cluster medium, it feels something called ram pressure, right? And if I explain this in a very simple way, think that you are riding a bike against the wind, right? So what you feel is you feel the wind, right, for you, and I mean you feel that particular wind for yourself. I mean that's what the ram pressure is, something not the exact same thing, but something like that. So when the galaxy is moving inside the galaxy cluster, most probably it should be moving towards the central region because of the gravity. It feels this intracluster medium as a ram pressure. We call that as a ram pressure, and that we expect that this particular ram pressure will trigger the star formation, right? And there are some other equations. You don't need to go through all these things, by the way, right? So what the idea is, this ram pressure stripping thing may take out some of the interstellar matter from the galaxy, so that it will completely stop the star formation of the galaxy, or it can go in the other way as well. Sometimes there should be active star formation, and this is one such example that one of these galaxy called Abel 3627 cluster, and inside this galaxy cluster there is one galaxy that moves through the cluster, and while it is moving through, it feels this ram pressure, and because of that, some of the gas that belongs to the galaxy is stripped out from the galaxy, and that's why you see this blue kind of line right here, right? And which will either lead to truncate the star formation, or maybe increase the star formation, which we don't know exactly, because these are areas that still under investigation. Now, what I was trying to do is study to quantify the impact of high density cluster environment on galaxies by measuring their star formation rate. So what I was trying to do is, I was trying to measure the star formation rates inside these galaxies in the galaxy cluster, and I basically was trying to see whether this star formation rate is increasing or decreasing from the center of the galaxy towards the outskirts, right? Let's think about the galaxy cluster as a circle, and you measure what happens to the star formation rates in the in galaxies inside this galaxy cluster from the center towards the outer region of this circle, right? Whether this star formation rate increase or decrease. Because if it is increased, then we can tell, okay, so that is maybe a clear indication that when a galaxy comes towards the central region, it will be, its gases may be stripped away, and due to the ram pressure, thing, or maybe due to any other effect, the star formation has stopped inside a galaxy cluster, right? So like that, right? Now, the things that probably should be interesting for you is, now we have a project, and I plan to measure the star formation rates of galaxies inside galaxy clusters. And the next question is, how can I measure those? Right? How can I measure the star formation rates? So I need to find a method for that. And the method is actually very, very basic, and you probably may have learned about this thing in A-level chemistry. So that is looking at this H-alpha line. So what actually happens is, if there is some star formation, active star formation going in a certain region, you will see a lot of H-alpha observations, right? So that is one of the fundamental methods of measuring star formation, right? And so what happens is, when you have this sort of star formation going on, you will see a lot of ultraviolet radiation coming out from these regions, and this ultraviolet radiation can ionize the surrounding hydrogen, right? So what happens is, when they are ionized, they will go into higher energy states, and then come down again for the lower energy states like this. And when this happens, there is a specific line that emits correspond to this much of energy. So that is called H-alpha line, right? And all of you, I guess, know this about this H-alpha line. And this line has a wavelength of 656 nanometers. So it is famous as 6563 angstrom line, right? And this is the line you should see, or you should have some H-alpha flux coming out from these regions if you have active star formation. Now this is the method that I am going to use. What you need to understand here is, now we have a problem and I have to solve it, right? And it's not an easy problem to solve. I am going to measure the star formation rates inside galaxy clusters. Now the fundamental thing is how to measure the star formation rates. Now, from the knowledge that I have about astronomy from the astronomy courses, I know that if I have star formation going on in a certain region, you will have a lot of ultraviolet emission which could ionize the surrounding hydrogen, and as a result of that, there should be some H-alpha emission in that region. And if I can detect this H-alpha emission, I can decide that there should be some star formation going on, right? So that's how you decide it, right? And so now I have decided, okay, I am going to measure the star formation rates. Now I have a mechanism. That means if I can detect some H-alpha flux, then I can conclude that there are some star formation in that particular region. Now the next question is, how can I detect these H-alpha photons, right? If there are. Now that's where you end up with the instrumentation. Now you need to find, you have to decide how to detect these H-alpha observations. Now what me and my supervisor did was, at that time, so we decided that, okay, this particular telescope would be the best one that we can catch some distance galaxy clusters. This is called this place is called Kitt National Observatory, and this particular telescope is called 4-meter telescope. The reason is that it has a mirror that has a diameter of 4 meters, and it can actually look at millions of light years away from the Earth, and the location is a mountain. The sky is very clear and a very dark place, and the telescope itself is famous for different discoveries, such as this galaxy rotation curves, which relates to the dark matter. Right now, we selected this particular telescope because it can observe these galaxy clusters that are so far away. And we were actually planning to look at the dwarf galaxies inside these galaxy clusters. And because of that, you need a very good telescope, right? In this level of telescope, right? And then, so this has a very nice camera, which is a CCD camera, which can detect and or catch the lights more effectively. And this is the structure of this camera chips. I'm not going to talk about all these details. And then the next thing is, now you have to detect the H alpha, you need to have some filters, right? And so here are the three filters that I have used. One filter is this red filter that is in a different color. And then I have another two narrowband filters right here. So the blue one and the green one, those are actually the two H alpha filters that I have used. Now, you probably think that this is actually another nice application, that things that you have learned. You probably think that why do I need two filters, two H alpha filters? Because H alpha is 6563 angstrom line, and you just need one filter, right, to detect that particular region. 6563 is around this region right here. But then you have another green one that is a little bit further away, right? Now, can anybody think why you need two filters like that? Why you need this second filter? Anybody have any idea? We have discussed about this particular effect, I guess, last 2 days. It is true that in the laboratory frame you have 6563 angstrom line, but what happens to these galaxies, actually they are moving away from us, right? Remember that we talked about that according to the Hubble law. And when they are moving away from us, they are actually redshifted, right? Now, when these galaxies are moving away from us, you need to think about that as well. Now, this is how you design an experiment or design a plan to solve a problem, right? So you have to think all these things. Otherwise, if you just select an H alpha filter and then you go and look at these galaxies that are millions of light years away from you, and then you look for H alpha filters, but you will never find those, right? Because when something is redshifted, this line is also shifted, the H alpha line, right? So you need to select the correct filter depending on the distance that you are looking at, right? Now that is why I basically have observed these 10 galaxy clusters, and this A426 and A96 images are the one that I have shown to you. And you can see that I have sometimes used, there are actually two filters that I have used for a reason. I'm not going to explain that here, but just look at this K1059 filter, and sometimes I have used K1060. That is due to the fact that their redshift is larger, and because of that, this 6563 angstrom line has shifted, right? Due to their redshift. Basically, they are moving away from us. Because of that, they are more, the line is shifted according to that redshift value, and because of that, you have to use a different filter to center this 6563 angstrom line. So, which means now you need to have the knowledge of that galaxies are moving away from us, universe is expanding, right? And this is what you are doing throughout this course, right? So we learned that these are moving away from us, but one day when you go for these actual observations, you need to consider that. And here are the locations. If you take a spherical map, these blue dots are the locations where I have observed the sky to look at these, I guess, 10 galaxy clusters at different times of the year. And then there are, several data reduction steps that I am not going to go through here. It's kind of, it's a 5-year work, so that I cannot explain it within a half an hour. So here are the original raw images, by the way, that comes out from the camera. And you can see that there are like these gaps in between the chips. That's because I have used a a camera that has several CCD chips. So you need to do some work to calibrate it and then collect all these chips together and stack those. There is a process that goes into here. And then you have to do like coordinate transformations, and you probably have learned this coordinate transformations in some of your courses, right? So this is the place that you use those, and then you have to decide the exposure time. So that again, based on what kind of things that you are looking at. And here is a sample image, and then there is a reason that when you get the POX H alpha flux, you need to do a image subtract, scaled image subtraction. So that's why you observe the same image from the R band filter as well, which is, I mean, you don't need to know all these things, just some information. And I can't remember whether I talk with you the seeing condition, astronomical seeing. I guess I did talk with you. So you have to consider that as well at the end when you do this scaling. Again, you don't need to know all this. And then this is like Fourier convolution, some kind of thing. And so we are actually doing very specific things here. And this image basically, by the way, is that central region where you have the BCG galaxy at the center. And what you do here is when you have a same galaxy cluster image through two filters, R band filter and the H alpha filter, we do something called image subtraction. One image is subtracted from the other. Basically, it's a pixel subtraction. And the idea is you can get the POH alpha flux, right? For example, this large galaxy right here, and you take the same image from the two filters and you do the subtraction. And once you do a subtraction, you will get this particular image right here, the subtracted image. All the objects that you do not have any kind of H alpha flux will go away in this image, and all the objects that you have some kind of H alpha flux will remain here. That flux will only remain. Now, if you look at these two galaxies and compare with the same galaxy right here, you can see most of the things are subtracted out, but there is still a small region right here, right? So those are the POH alpha flux, which tells you these are the regions that you have active star formation going on in this galaxy. And if you can see, I don't know whether you can see it, I have marked some of the red squares right here, and corresponding red squares, you don't see anything in red squares right here. That means those objects do not have any kind of H alpha flux, so they are subtracted out completely. So that's to show you that I did a nice image subtraction that will give me only H alpha flux, right? Now, once you are in this particular situation, then you can measure this flux and convert it to a star formation rate, and that so there are huge some kind of work that you need to go for object detection, and you need to decide what are galaxies and what are stars, and there are statistical methods for that. You don't need to know all of these things. And sometimes these large galaxy at the center, and this is that huge galaxy at the center in the Abell 426 galaxy cluster, and you need to model that galaxy and subtract out to look at whether there are other galaxies behind that particular galaxy, so those kind of things. So I'm not going to go through all these things. I mean, if somebody need to know in detail, I will explain it later, but so I just need to show you how this knowledge that you acquired here is actually used in some place, right? And here is, by the way, this magnitude equation that you learn, and it will be modified here to find the absolute magnitudes of these galaxies. And then, so here are the equations that are used to find the star formation rates, which we did not talk. We are not going to talk in this particular class. And then, so what I have seen is right here. So after all, I have measured the star formation rates of the galaxy cluster. So that is from central region to outer region, what happened to the star formation rate in the log scale, and this is what I have obtained. Basically the star formation rate seems to be increasing towards the outer region. And then here is another measurement called equivalent width that I have measured, and here are some other, specific, something called specific different measurements that you look at to see whether star formation rate increase or not, and then you divide the sample into giant galaxies and the dwarf galaxies based on certain criteria, and check whether how the dwarf galaxies distributed in this in galaxy clusters, and then see what happens to dwarf galaxies in terms of the star formation rate, and they keep increasing. And surprisingly, when I was looking at the giant galaxies, I didn't see much change in the star formation rates for large galaxies, and dwarf galaxies clearly shows an increase in the star formation rate. And this is actually, by the way, a new finding, still have not published in anywhere, so still working on. And so these are like, I don't have time to explain you everything, so some kind of, explanations. Now, finally, there is a conclusion that what happened to the star formation rates with the time and the future work like that. And this was, I was working with the University of North Dakota, and I was funded by National Optical Astronomy Observatory for this telescope time and staying there and all of these things. And then also one of the grants from NASA to complete this work at the end. And so that's it. So the aim is that just to show you how this knowledge that, so let me stop sharing this, show you how this knowledge is used at a certain point, and just to convince you that what you are learning right here is actually important, right, at a particular day. Now, I will upload this presentation to the LMS as well. And if anybody need like more into detail about this, let me share this YouTube link. So this original presentation is available in YouTube. You don't have to look at that because I mentioned the things that are important, but if you need to gain more knowledge, let me just share the presentation with you. And while I'm sharing this, anybody have any questions up to here about this? Right, so let me share this with you. And if you do not have any questions up to here, so I'm going to stop the lecture after having this link for you. And so you are free to go here and look at this lecture if you are interested. It means probably have a little bit more details for each and everything that is mentioned in the presentation. Otherwise, the presentation is the same. And right, so I guess starting from the next week, I am planning to start these lectures about the general relativity. So there are a lot of things that we have to do in that side as well. And so everything that we learn up to now, you will probably have another tutorial for the lectures that I did up to today. And I will probably upload it at some point within the next week. And I guess that's it for today. If anybody have any questions, I can answer. Right. The other thing is, let me